Good morning, students. This is lecture number 29. It is based on special types of LPPs, and today we are going to learn the assignment problem. Now, the assignment problem is a special class of the linear programming problems, and it is actually a special case of the transportation problem that we have studied earlier. Now, in this case, the transportation problem, when the number of sources, which is usually equal to m, and the number of destinations, which is usually equal to n, when they are both same, and also all the supplies at the sources and all the destination the demands at the destinations, they are all equal to 1. So, the generalized transportation problem, when it satisfies these conditions, then it is said to be a assignment problem. Now, let us look at it mathematically. The objective function to be minimized is summation over j equal to 1 to n, summation I is equal to 1 to n, Cij Xij, which is subject to summation j equal to 1 to n, Xij is equal to 1, and summation I is equal to 1 to n, Xij is equal to 1. Now, Xij's, they should be either 0 or 1 for all I and j going from 1 to n. Now, the constraints are actually the row sums equal to 1, and the second set of constraints is the column sums equal to 1.Cij's are the real numbers which denote the cost coefficient corresponding to the matrix that we have. Now, in case the number of rows is equal to the number of columns, then it is called as a balanced transportation problem or a balanced assignment problem. Whereas, if the number of rows is not equal to the number of columns, then it is called as a unbalanced transportation problem or a assignment problem. However, in case the problem is an unbalanced problem, then as I have already explained in the case of the transportation problem, the dummy rows or the dummy columns have to be added, so that the problem when it is an unbalanced problem that becomes a balanced one. Now, let us consider the following example. Let us suppose that there are n workers W1, W2, Wn, and these workers are supposed to be assigned to n jobs J1, J2, Jn, and let us suppose that Cij, which are real numbers, is the cost of assigning the ith worker Wi to the jth job Jj. Now, since our Xij's are the decision parameters, we can define our XRP as 1 if Wi is assigned to Wr is assigned to Jp, and 0 if Wr is not assigned to Jp. So, it becomes a 0-1 programming problem, that is, the decision parameters are taking only two values, either 0 or 1. Also, the row sums is equal to 1, that is summation j is equal to 1 to n, Xij is equal to 1. This implies that the ith person is assigned to a job, and the column sum, that is Xij, I goes from 1 to n is equal to 1, implies that the jth job is assigned to some worker. So, this assignment has to be uniquely defined. In other words, no person or job remains unassigned, and the problem becomes we have to find out the arrangement which minimizes the total cost of the assignment denoted by F. So, in order to solve this special kind of problem, we need a theorem which states the following: let Cij dash is equal to Cij minus Ui minus Vj for all I and j, where Ui and Vj are real valued functions of I and j respectively, and let f dash is equal to double summation Cij dash Xij be the minimum for the values of Xij given by Xij is equal to Xij 0. Then f is equal to double summation Cij Xij is also minimum for Xij is equal to Xij 0. The meaning of this theorem states that if we want to subtract some constants from theCij's, which is the cost coefficient matrix, then the optimality will not be affected. So, this theorem allows us to subtract any kind of a constant from the cost matrix. This is the basis based on which the method for solving the assignment problem has been designed. To solve the assignment problem, the well known Hungarian method is there, and it has the following steps. Step number 1 is, from the given cost coefficient matrix, identify each row's minimum and subtract it from all entries of that row. What does this mean? This means that suppose from the first row, find out its minimum value and subtract that minimum value from all entries of that row. And this has to be done for all the rows, and once all the rows are completed, then from the remaining entries repeat this for the column, and that is the second part of the step number 1, that is, from the resulting matrix identify each column's minimum and subtract it from all entries of that column. Now, I will explain this method side by side with the help of an example. So, let us suppose the workers that we have, the 5 workers W1, W2 up to W5, they have to be assigned to 5 jobs, that is J1, J2, Jn, and the cost coefficient matrix is given here in this table. So, what we need to do is we need to find out the minimum of each of the rows. So, as you can see that from the first row the minimum is 7, it is written in a blue color, minimum of the first row is 7. So, we need to subtract 7 from all the entries of the first row. Similarly, the minimum of the second row is 6. So, we need to subtract 6 from all the entries of the second row, and like this we need to subtract 6 from all entries of the third row, and we need to subtract 8 from all the entries of the fourth row and 5 from all the entries of the fifth row. And when we perform these operations, this is the resulting matrix that we get. So, as you can just check, 8 minus 7 is 1, 10 minus 7 is 3, 14 minus 7 is 7, 12 minus 7 is 5, and 7 minus 7 is 0. And like this you can check all the rows have been used by subtracting the minimum of each row. And this means that in each row somewhere or the other you will get a 0 entry. Now, once you have done this for all the rows, you have to repeat the process for the columns, and you can see that in the first column the entries are now 1, 0, 6, 3, 0. So, what is the minimum? Minimum is 0. Second row, second column 3, 10, 5, 0, 5. So, minimum is 0. Third one 7, 7, 0, 5, 10. Minimum is 0. And the fourth column is 5, 6, 2, 4, 4. Here the minimum is 2, and like this the last column also minimum is 0. So, again the same thing we have to do, that is we have to subtract 0 because that is the minimum. So, that will not affect, only the fourth column will be affected because the minimum of the fourth column is 2 and we have to subtract 2 from all entries of the fourth column. So, the resultant matrix will look like this. Please check 1 3 7 3 0, 0 10 7 4 4, 6 5 0 0 1, 3 0 5 2 0, 0 5 10 2 and 9. Now, you will observe that in some rows or columns 0 is appearing more than once, does not matter. Now, the next step has to be implemented. So, this first step is completed. Now, what is the second step? The second step says we have to draw horizontal and vertical lines which can cover all the 0 entries. What does this mean? It means that we have to we have to identify all the zeros and we have to delete those rows. So, the step 2a says mark the 0 entry in each row and delete the column containing that 0. Of course, if there are more than 2 zeros in a row, skip that row. And the step 2b says if all the zeros are covered, go to step 3, else go to step 2c. And 2c says mark the 0 entry in each column and delete the row containing that 0. If there are more than 2 zeros in a column, skip that column. Now, what does this mean? Again, coming back to our example, let us look at the first row. In the first row, the row says 1 3 7 3 0. So, there is only 1 0 in this row, in the first row. So, we have to draw, we have to mark this 0, and after marking 0, we have to draw a vertical line, that is which is going to cross the last column, the fifth column. Once this is done, then we come to the second row. From the second row, we find 0 is at the first place, and this means that we have to delete or draw the vertical line in the first column. Then comes the third row. Now, in the third row there are 2 zeros. So, according to the step 2a, we are just not supposed to do anything with the third row and just skip this row, and then we go to the fourth row. So, in the fourth row we find 0 is there, and therefore, we have to draw a vertical line which is going to contain that 0. Again, coming to the fifth row, we find that there are no zeros. So, again you do not have to do anything, and for this part of the step 2 is over. Once you have completed all the rows, that is you have scanned all the rows, then you have to repeat this process with the columns. So, this is what happens. The first column is already crossed, so you do not have to do anything. Second column already crossed, so nothing to be done. Look at the third column. In the third column we have a 0. So, therefore, we have to draw a horizontal line which will cross this 0, and that is what we have done here in this last table. As you can see, in the last table 0 has been crossed out. So, the third column, the 0 was found in the third column, and therefore, it has been crossed out with a horizontal line. Remember, when you are scanning the rows and you find a 0, you have to draw a vertical line, and when you are scanning the columns and you find a 0, you have to draw a horizontal line. So, once this is done, then we move to the step 3. In the step 3, if the minimum number of horizontal and vertical lines covering all the 0 entries is less than or equal to n, and what is n? N is the size of the problem, that is, in our case n is 5. Then this means that optimum solution is achieved. However, if this is not true, then we have to go to step 4. Now, what does it mean? Look at this table that we got in the previous step. Here we find that the number of lines is equal to 4. As you can see, there are 1, 2, 3, 4 lines. There are 3 vertical lines and 1 horizontal line. So, there are total 4 lines crossing the zeros, and the dimension of the problem is 5, which means 4 is not equal to 5. Therefore, the stopping criteria is not satisfied, and we have to do the next step, that is the step number 4. Now, the step number 4 says select the smallest uncovered entry and subtract it from every uncovered entry. Now, you will see that there are some entries which were not crossed out. So, we have to pick out the one which is the smallest from the uncovered entries and subtract it from all the uncovered entries in the table. Once you have done this, then the 4b says add this smallest uncovered entry to every entry at the intersection of the covering lines. So, there are covering lines that we have drawn, there are some of the intersection points. At those intersection points, we have to add the smallest entry, and the C part says that all the remaining entries have to be left unchanged. So, once this is done, again go to step 2 and repeat the process. So, let us look at this step 4 again. Here the smallest uncovered entry is 2. What do you mean by uncovered entry? Those entries which have not been crossed out at the moment. So, the uncovered entries are 7, 3, 7, 4, 5, 2, 10 and 2, and among these 2 is the smallest. So, therefore, what we are going to do? We have to subtract 2 from all the uncovered entries, and once you do this, this is what you get. 7 minus 2 is 5, 3 minus 2 is 1, 7 minus 2 is 5, 4 minus 2 is 2, 5 minus 2 is 3, 2 minus 2 is 0, 10 minus 2 is 8 and 0 minus 0 is 0. So, all the uncovered entries have been 2 has been subtracted from all the uncovered entries. The next part of the step says that we have to add 2. Why 2? Because 2 was the smallest uncovered entry. So, we have to add 2 to all the intersection points of the horizontal and the vertical line. Now, there are 3 places where the verticals and the horizontal lines are intersecting. What are those 3 points? They are 6, 5 and 1. So, therefore, we have to add 2 to all these 3 entries, and this is the resulting matrix that you get. This completes the 4th step. Again, we have to go to step 2 and repeat the process. On the leftmost, we have the table that we have got 1, 3, 5, 1, 0, etc. Again, we have to repeat step 2, that is, we have to determine the zeros at each of the rows. So, in the first row we find a 0 in the last entry, that is the 5th entry. Therefore, we will draw a vertical line at the last column. Then again in the second row we find there is a 0 entry at the first place. So, we again need to draw a vertical line at the first column. Then coming to the third column says there are 2 zeros. So, therefore, we have to skip this line, and again in the fourth row we find that there is a 0 entry. So, therefore, the same procedure has to be repeated, and once we complete this, then we find that the number of lines, that is the number of horizontal and vertical lines, is 5, and which is equal to the dimension of the problem, which is equal to 5. This means that our stopping criteria has been satisfied. So, therefore, our stopping criteria is satisfied, and if you look at the original data that was given and you look at this final table that you have, this means that the assignment, that is we were looking for the optimum assignment. So, the optimum assignment is the one which is corresponding to the 0 entries in the last table. So, W1 should be assigned to J5. Why is this so? W1 is assigned to J5. Why? Because there is this 0 entry over here. Similarly, W2 is assigned to J1. Why is this? Because there is a 0 entry over here. And similarly, W3 is assigned to J3, and W4 is assigned to J2, and W5 is assigned to J4. So, this is the optimum assignment. Now, let us look at the cost. The cost corresponding to the assignment of worker 1 to the 5th job is 7. Why did this, from where this 7 has come? This has come because this 7 is corresponding to this entry. Similarly, W2 is assigned to J1. So, this 6 has come because of this entry, and like this you will find that the cost corresponding to W3 J3 is 6, and the cost corresponding to W4 J2 is 8, and the cost corresponding to W5 J4 is 9, and therefore, the total cost will be the total of all these costs, which is 7 plus 6 plus 6 plus 8 plus 9, and that comes out to be 36. So, the overall cost of the optimum assignment is 36. So, with this I have an exercise for you. A departmental head has 4 subordinates and 4 tasks to be performed. The subordinates differ in efficiency and the tasks differ in their difficulty. The departmental heads estimates of the time in hours that each subordinate would take to perform these tasks is given in the table. How should the tasks be allocated to the subordinates so as to minimize the total time taken to perform the 4 tasks, assuming that one person can only be assigned one job? Now, the data in this problem is given as follows, that there are 4 subordinates A, B, C, D, and there are 5 tasks 1, 2, 3, 4, 4 tasks 1, 2, 3, 4, and we have to assign the subordinates the various tasks, and the data is given in this table. I would want you to please solve this exercise. I have given the answer. A should be assigned to 1, B should be assigned to 3, C should be assigned to 2 and D should be assigned to 4, and the total time is 41 hours. So, just as we have learnt in this assignment problem, please use this Hungarian method to solve this problem. So, using the Hungarian method, please solve this example the way in which we have learnt in this lecture. Thank you.